When installing a NEMA Type 2 service entrance rated motor controller, specifically a 50 horsepower, 3-phase 480 volt unit, installers have specific responsibilities to prevent metal chips and shavings from contaminating the circuit breaker and solid-state low-voltage control equipment within the enclosure. To accomplish this, several measures should be taken. Firstly, utilize a hole saw or a step drill specifically designed for cutting metal enclosures. These tools are designed to minimize the creation of burrs and shavings during the cutting process. The design of these tools often incorporates features that help to contain and direct the metal debris, reducing the likelihood of it entering the enclosure. Secondly, it is important to immediately remove any metal chips and shavings that are produced. This can be accomplished using a vacuum cleaner or compressed air. A vacuum cleaner is effective for collecting loose debris, while compressed air can dislodge particles that may be clinging to surfaces. Take care when using compressed air to ensure that the debris is directed away from sensitive components. Thirdly, a thorough inspection of the interior of the enclosure is essential after punching the holes. Carefully examine all surfaces for any remaining metal chips or debris. Use a brush, vacuum, or compressed air to remove any contaminants that are found. Pay particular attention to areas around the circuit breaker and solid-state control equipment, as these components are especially susceptible to damage from metal contamination. Regarding the acceptability of a hole saw versus a pilot hole and hole punch, a hole saw is generally considered the best practice for punching holes in metal enclosures. This is because a hole saw provides a cleaner cut compared to the traditional method of drilling a pilot hole and then using a hole punch. The cleaner cut produced by a hole saw results in fewer burrs and sharp edges, which can trap metal debris and potentially cause damage to the equipment. The NEC, or National Electrical Code, does not explicitly address the term contamination exclusion. However, it does emphasize the importance of performing electrical installations in a neat and workmanlike manner. This requirement is outlined in NEC Section 110.12. The implication of this section is that installers must take reasonable precautions to prevent metal chips and shavings from contaminating the circuit breaker and control equipment. These precautions should include the use of appropriate tools, proper cleaning procedures, and careful inspection of the enclosure. The NEC provides guidelines for ensuring the safe and reliable operation of electrical systems, and preventing contamination is an integral part of maintaining the safety and reliability. To further elaborate on the selection and use of tools for cutting conduit holes, consider the specific advantages and disadvantages of each option. A hole saw, as mentioned, is generally preferred for its ability to create clean, precise holes with minimal burrs. When selecting a hole saw, ensure that it is specifically designed for cutting metal. These hole saws typically have hardened teeth and a suitable tooth pitch for efficient metal removal. It is also important to use the correct cutting speed and lubricant to prolong the life of the hole saw and achieve the best results. A step drill, also known as a unibit, is another excellent option for creating holes in metal enclosures. Step drills are versatile tools that can create holes of various sizes, making them suitable for a range of conduit sizes. They also produce relatively clean holes with minimal burrs. One advantage of step drills is that they are less likely to bind or grab the metal compared to traditional twist drills. When using a step drill, start with a small pilot hole and gradually increase the hole size by applying gentle pressure and using a suitable cutting lubricant. A pilot hole and hole punch is a traditional method for creating holes in metal enclosures, but it is generally less preferred than hole saws or step drills. This method involves drilling a small pilot hole and then using a hole punch to enlarge the hole to the desired size. One of the main disadvantages of this method is that it can create significant burrs and sharp edges, which can trap metal debris. Additionally, the hole punch may distort the metal around the hole, making it difficult to achieve a clean, precise opening. If this method is used, it is essential to carefully debur the edges of the hole to remove any sharp edges or projections. The proper technique for using compressed air to remove metal chips and shavings is also important. When using compressed air, always wear appropriate eye protection to prevent debris from entering the eyes. Direct the compressed air at an angle to the surface to dislodge any loose particles. Avoid directing the compressed air directly at sensitive components, as this could potentially damage them. It is also advisable to use a vacuum cleaner in conjunction with compressed air to collect the dislodged debris. The importance of regular maintenance and cleaning of electrical enclosures should also be noted. Over time, dust, dirt, and other contaminants can accumulate inside the enclosure, potentially affecting the performance and reliability of the equipment. Regularly inspect the interior of the enclosure and clean it as needed. Use a vacuum cleaner or a damp cloth to remove any accumulated debris. Avoid using harsh chemicals or solvents, as these could damage the components. In addition to preventing contamination, it is also important to ensure proper grounding and bonding of the electrical equipment. Grounding and bonding provide a path for fault current to flow back to the source, helping to protect personnel from electrical shock and prevent equipment damage. Refer to the NEC for specific requirements regarding grounding and bonding. Following these guidelines will help to ensure the safe and reliable operation of electrical systems and prevent potential hazards. The installer plays a crucial role in maintaining the integrity of the electrical installation and protecting the equipment from damage. Another aspect to consider is the type of conduit being used and its compatibility with the enclosure. Different types of conduit, such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit, have different characteristics and installation requirements. Ensure that the conduit is properly sized and supported, and that appropriate fittings are used to connect the conduit to the enclosure. The use of proper fittings is essential for maintaining a secure and watertight connection. When selecting fittings, consider the environmental conditions and the type of conduit being used. Also, be sure to install the fittings according to the manufacturer's instructions. Furthermore, it is imperative to verify that the conduit is properly grounded and bonded to the enclosure. This can be achieved by using grounding bushings or bonding jumpers. Grounding bushings provide a secure connection between the conduit and the enclosure, ensuring a continuous ground path. Bonding jumpers are used to connect different sections of conduit or to bond the conduit to other metal structures. The NEC provides specific requirements for grounding and bonding of conduit systems, so consult the code for detailed guidance. Another area of concern is the potential for moisture to enter the enclosure. Moisture can cause corrosion and damage to electrical components. To prevent moisture intrusion, ensure that the enclosure is properly sealed and that all openings are adequately protected. Use weatherproof fittings and sealants to prevent water from entering the conduit system. Additionally, consider installing a breather drain in the enclosure to allow moisture to escape. A breather drain is a small device that allows air to circulate in the enclosure while preventing water from entering. Also, make sure to select an enclosure that is rated for the environmental conditions in which it will be installed. Enclosures are available in various NEMA ratings, which indicate their ability to withstand different environmental hazards such as water, dust, and corrosion. Select an enclosure with a NEMA rating that is appropriate for the intended application. It is also crucial to properly torque all connections in the electrical system. Loose connections can cause overheating and arcing, which can lead to equipment failure and even fires. Use a calibrated torque wrench to tighten all connections to the manufacturer's specified torque values. Periodically inspect the connections to ensure that they remain tight. Retorque any loose connections as needed. By following these practices, installers can help ensure the safe and reliable operation of electrical systems and prevent potential hazards. The importance of ongoing training and education for electrical installers cannot be overstated. The electrical industry is constantly evolving, with new technologies and regulations being introduced regularly. Installers must stay up to date on the latest developments to ensure that they are performing their work safely and effectively. Participate in continuing education courses and workshops to enhance your knowledge and skills. Read industry publications and attend trade shows to learn about new products and technologies. By investing in ongoing training and education, installers can improve their competence and advance their careers. Remember, electrical safety is paramount. Always follow safe work practices and procedures to protect yourself and others from electrical hazards. To energize circuits before working on them, use appropriate personal protective equipment, and never take shortcuts. If you are unsure about any aspect of an electrical installation, consult with a qualified electrician or engineer. By prioritizing safety, installers can help prevent accidents and injuries. Let's delve deeper into the specifics of solid-state low-voltage control equipment and its vulnerability to contamination. Solid-state devices, such as programmable logic controllers, variable frequency drives, and other electronic components, are highly sensitive to foreign particles. Metal chips and shavings can cause short circuits, overheating, and premature failure of these devices. The small size and intricate circuitry of solid-state components make them particularly susceptible to damage from contamination. Even a tiny metal particle can bridge the gap between conductors, creating a short circuit. This can result in immediate failure of the device or gradual degradation of its performance. Overheating is another common consequence of contamination in solid-state devices. Metal particles can impede the flow of heat away from the components, causing them to overheat. Overheating can damage the internal components of the device, leading to reduced lifespan and eventual failure. In addition to electrical and thermal damage, contamination can also cause physical damage to solid-state devices. Sharp metal particles can scratch or puncture the delicate surfaces of the components, compromising their integrity. To prevent contamination of solid-state devices, it is essential to follow the previously mentioned precautions diligently. Use appropriate tools, clean up debris immediately, and inspect the enclosure thoroughly. Consider using anti-static mats and wrist struts to prevent electrostatic discharge, which can attract and hold metal particles. Furthermore, it is advisable to protect solid-state devices with conformal coatings or other protective measures. Conformal coatings are thin layers of insulating material that are applied to the surface of the components. These coatings provide a barrier against moisture, dust, and other contaminants. They also help to prevent corrosion and improve the reliability of the devices. Another important consideration is the proper ventilation of the enclosure. Solid-state devices generate heat during operation, and inadequate ventilation can lead to overheating. Ensure that the enclosure has sufficient ventilation openings to allow for proper airflow. Consider using fans or other cooling devices to enhance ventilation. Also, be mindful of the ambient temperature in which the enclosure is installed. High ambient temperatures can exacerbate the effects of overheating. Select an enclosure that is rated for the maximum ambient temperature in the intended application. Finally, it is crucial to implement a regular maintenance program for electrical enclosures containing solid-state devices. Inspect the enclosures periodically for signs of damage, corrosion, or contamination. Clean the interior of the enclosure as needed, and replace any damaged or worn components. By implementing a proactive maintenance program, you can help to prevent costly repairs and downtime.